I'm Ethan Wang and my partner is Kaashvi Sehgal. For our project, we parallelized the artificial bee colony algorithm using OpenMP and OpenMPI. The artificial bee colony algorithm is an optimization algorithm which simulates the foraging behavior of bees. There are three phases in the algorithm which are repeated over a number of iterations. Each food source is a parameter vector x. At the beginning, each food source's parameter vector is initialized to a random value. The number of food sources is the number of potential solutions that the algorithm keeps track of at one time. The colony size, or the number of bees, is twice the number of food sources. Half the bees are employed bees and the other half are onlooker bees. In the employed bee phase, each bee visits a different food source. There is one food source per employed bee, and searches the immediate area around the food source. If it finds a better solution, it updates the current value of the food source to the one it found. In the onlooker bees phase, based on the fitness of each food source is assigned a probability of being chosen by an onlooker bee. Better food sources have a higher probability of being chosen. Each onlooker bee chooses a food source to visit based on this probability distribution. In this phase, a food source can be visited multiple times by different bees. The food sources with better fitness are visited more often and explored more. Each food source has a max number of tries it can be improved. If the number of attempts to improve the food source is exceeded without further improvement, the food source is abandoned and reinitialized to a random value. This is how the algorithm avoids converging to a local minimum. This is the objective function that we will be testing our sequential and parallel implementations on. It's called the egg holder function and is difficult to optimize because of the large number of local minimums. We tried two main ways of parallelizing our algorithm. In the first way, we parallelized across each phase. The employed bees phase was easy to optimize since every bee visited a different food source. There is no sharing or overlapping of the data in this phase, so each thread can operate independently. However, the onlooker bees phase was more difficult to optimize. Since multiple bees can visit the same food source, it is possible that the threads need to synchronize and apply updates to food sources in order. Therefore, to parallelize the onlooker bees phase, we needed to make some trade-offs between operating on stale data and applying multiple updates at once. In this implementation, there was lots of overhead since each of the parallel sections do small amounts of work and between each phase is an implicit barrier. In our second attempt to parallelize the algorithm, we parallelized across the entire iteration instead of multiple phases. This approach was less optimal for accuracy since there is more computation on stale data. However, this approach minimizes overhead, as each parallel section executes both the employed bees and the onlooker bees phase. At the end of each iteration, the values for each of the threads updates are compared, and the best one is selected for further optimization on the next iteration. We ended up going with this implementation. In the OpenMP solution, for each thread, we ran the employed bees phase and the onlooker bees phase in parallel. At the end of each phase, the thread with the best food source is chosen, and all the other threads update their food source to the new best one for the next iteration. These are the results for our OpenMP implementation. We tested on a few different colony sizes. The larger the colony size, the more work per iteration. We can see that when the colony size is 100, the parallel implementation is significantly slower than the sequential. This is because of the overhead of initializing the threads dominates computation time. When colony size is 1,000, there is a very slight speedup, but overall the performance is still comparable to the sequential version. Only when we move to a colony size of 10,000 do we see the benefits of parallelization. The work in the parallel section becomes large enough to justify the overhead of parallelization. We get a max speedup of around 8 when using 128 threads, which is still much less than ideal. In the OpenMPI version, at the end of each iteration, each of the non-root threads would send their best food sources found to the main thread. The main thread would receive all these food sources and determine the best one. Then the best food source is broadcast to all the other threads, and the other threads update their own food sources. In contrast to the OpenMP version, we see significant speedup occurring across all three colony sizes using OpenMPI. This is because in the OpenMP version, we are spawning and joining threads every iteration. In the OpenMPI version, we initialize all the threads at the beginning and they continue to run throughout the entire program. While the message passing requires some synchronization, the overhead was much lower than the OpenMP implementation since the frequency of messages sent and the sizes of messages were small. For the colony size of 10,000, we achieved almost perfect speedup, even with 128 threads. In general, increasing the colony sizes increases the accuracy. This is because with a larger number of possible solutions, we are able to randomize more and adjust the solutions more to get closer to the optimal solution. Additionally, we can see that the sequential version is the most accurate across the board. This is because the sequential version never operates in stale data, whereas the parallel implementations are not as optimal. However, as colony size increases, the error rate drastically decreases to the point where the parallel implementations almost perform as well as the sequential version in terms of accuracy. In conclusion, the OpenMPI implementation offered the best speedup since it had minimal overhead in our application. We were able to achieve almost perfect speedup with only minimal loss to accuracy.